In this video clip, it's a great pleasure to welcome my colleague, Professor Charlie Lineweaver, who's an astrobiologist here at the ANU, who's published a lot of work about the question of where in the galaxy or the universe would you expect to be the best places for life to form. So Charlie, thanks for coming. We live in a rather boring part of our own galaxy. We're in the outskirts of a spiral galaxy in a planet orbiting a dwarfish yellow star. Is that the sort of place you'd expect life to form?
Well, since we don't have much evidence of life elsewhere, the answer would have to be yes, kind of. I think one way to look at this is, where is life on Earth? You know, often when you do science, you say, oh, what about the life elsewhere in the universe? But I like to say, well, what about life on Earth? Is there life everywhere on Earth? And certainly not. We are, for example, you and I live on the surface of the Earth, and that is a good reason for it, because about 3 kilometers down, it's too hot for life. And out in the void of outer space, it's hard to make life out of nothing. So most of the universe is nothing, and so I don't think it's any accident that we are on a surface of a planet where the densities are high and the temperatures and pressures are consistent with liquid water. But you asked about the galaxy. Well, the galaxy is about 12 billion years old, and it started out with low metallicity, as you may have talked about earlier in the course. So at low metallicity, there's not enough stuff around to produce a rocky planet, if you think that rocky planets and water is necessary. For example, water, you and I are made out of water. You need hydrogen was made by the Big Bang, but the oxygen in our water had to have been produced by stars. So the first billion or so years, there wasn't any oxygen in the universe, very much at all. And you couldn't make a rock like this. This is a piece of the Earth that's made out of silicon and oxygen, both of which did not come out of the Big Bang, but had to be formed in stars. So it's a little like the galaxy had big, massive stars producing lots of metals, and then slowly those metals eked their way out, diffused their way out to increase the metals, and finally, when you get about further out, and after a long time, you have enough metals to produce a rocky planet as big as the Earth, and they have to be somewhat close to the size of the Earth, because otherwise you can't hold an atmosphere. And if you can't have an atmosphere, you can't have liquid, and we think you need liquid for life.
But if you're saying we need lots of heavy elements, the outskirts of a galaxy like our own has been a relatively late place to acquire heavy elements. The heavy elements would have happened first in the middle of our galaxy.
That's true.
And even earlier than that in the giant elliptical galaxies, which also contain a lot more stars than a galaxy like our own. So would you expect us to be latecomers, and then in fact most life would be living in the central regions of our galaxy where there are more stars, more heavy elements, or even better in the middle of giant elliptical galaxies?
Well, I think the answer to that is, like so many things in biology, yes and no. A good analogy is, one danger of being close to where those elements are being produced is that they're being produced by supernova going boom. And when you're too close to a supernova, within, I don't know, a light year or 5 light years, depending on the size of the supernova, that is not conducive to the billions of years that you need to produce, I guess, what you call complex life. So one analogy is, there's a fire, and the fire is making ashes. And if you get too close to the ash, you need those ashes to make life, or a planet, a rocky planet. If you get too close to the fire, then you get burned and your life goes extinct. If you're too far away, you don't have the ashes that you need. And so somehow there's this boundary, almost like a metallicity habitable zone, not to do with temperature, but has to do with metal production, that this boundary has increased and gotten further out, and as the metals have spread, it's like fertilizing the galaxy with the metals needed to produce rocky planets in the first instance, and water and life in the second instance.
So by your best calculation, do we live in this nice Goldilocks zone?
Yes. My best calculation says if you were too close to the center of the galaxy, there are too many supernovae to allow for a billion years of peace during the evolution of life. And if you're too far away, you don't have enough metals. So somewhere in that Goldilocks, between those two zones, is where the sun is.
Now, the vast majority of stars in our galaxy are not like our sun. Our sun is a yellow dwarf star, a G-type star, but in fact the vast majority of stars are much smaller, cooler, redder. They're the so-called red dwarf stars, and they outnumber all other stars in our galaxy, and probably every galaxy, by a huge factor. So it might seem a bit odd that we're actually in orbit around such a big star. Would you expect life around these red dwarf stars?
Well, again, the answer is yes and no. Let me tell you the information, my thoughts on this. And that is, First of all, the sun is more massive than about 95% of all stars. And we wrote a paper comparing the sun to other stars precisely to figure out, is there something unique about our sun that would allow life to exist here and not elsewhere? And you're right, if you just say, oh, stars, 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 then it would be M dwarfs, these small stars that are 30% or even 10% the mass of the sun, which are the most numerous. And if life just formed around any old star, then we would expect to find our star being an M dwarf. That's not the case. We find ourselves around a very massive star. Well, but it's about a 2 sigma effect. And so it might be a coincidence, or it might be something that's significant enough to need an explanation. If you do need an explanation for why the sun is so massive, it might be the following. And that is, in order to kickstart life, you need some photons. You need energetic photons. And we know that stars as massive as the sun produce UV radiation in abundance that when it hits chemicals, it pumps electrons up, and then that is energy that can be used to do something interesting, to get life started somehow in ways we don't yet understand. If you're around an M dwarf, all you're seeing is red light, and that red light is often not enough to kick electrons up to high enough orbits to get life started. That might be one possible explanation for why we live around such a massive star.
So is there anything else unusual about our sun that might make it a particularly good place for life, or do you think it's...
Well, we looked at about 10 features of the sun, and the mass was one thing that stuck out at about 2 sigma level.
And 2 sigma meaning it's about 95% of stars are different from that. Are
less massive than the sun. The other thing where it started out, where it seems to maybe stick out, and that is here's our galaxy, and here's the central black hole, 4 million solar masses, and we're about 8 kiloparsecs, about 30,000 light years, and we're going around every 250,000 years. 250 million years, sorry. And the orbit of the sun, compared to other stars whose orbits we can estimate, seems to be more circular than the other stars. And so maybe there's something to do with circularity, but it's not a big effect, and so we don't want to read too much into this.
So it could be if the orbit was a more elliptical one, that might bring us closer to the middle where it's dangerous, or further out, or something like that, perhaps?
That's right, that's right.
So what you're saying is that as far as you can tell, our planet is about where you'd expect life to be.
Well, recently we found that it looks like almost a requirement for forming a star is the formation of the debris disk around a star, which forms planets. So we think the latest evidence suggests to me and many of my colleagues that planet formation is just a natural part of star formation, and we should expect some type of solar system around every star out there. That means that rocky planets like the Earth, or like Mars, like Venus, are probably ubiquitous in the universe. Then you have to ask the question, well, if you have a rocky planet, what's the probability of forming life there? And that gets more complicated. That has to do with chemistry and not the physics that you and I are so comfortable talking about.
So let me finish off by asking the question I will ask Brian later on. Mm-hmm. We've discussed in this part of the course the arguments for and against life in space. What's your personal feeling on this? Do you think we live in a universe that's full of life, or are we almost alone?
Well,
feeling.
Well, it's based on more than a feeling. I'm a scientist, so I don't like to have my feelings or don't give too much credence to my feelings. I like to say, what is the evidence? One thing that I've been giving talks about is why we should not expect humanoid life, not the kind of life that you see in Hollywood movies, for example, with 2 eyes and looks like a human being, or in human-like intelligent life. And I could give a long argument about why we shouldn't expect that. As to the question of life, that's much more difficult because we don't really know what life is. For example, if you ask a biologist if our viruses are alive or prions are alive, they say, well, maybe, I don't know. And so the definition of life really is disturbingly poorly understood. And so if that's the case, then your question is equally disturbingly ambiguous. That said, I'm one of the people who like to say, well, anytime you have a far from equilibrium system that, like a convection cell, you could call that life. But then people say, well, there's no information in a convection cell. And I say, well, maybe stars form molecules which then allow other stars to form. And so you have some type of replication there with modification. I can wave my hands a long time. And that just tells you the level of speculation that is associated with the question of is there life elsewhere in the universe. That said, yes, I think there is life elsewhere, but my definition of life is much more general than most biologists are comfortable with.
Well, thank you very much.
You're welcome.